Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 44, part A, and we are discussing bivariate transformations, and this is part 3. So in the previous videos, we've reviewed the bivariate transformation theorem. This is a theorem for one-to-one functions of the two variables. This is also called the bivariate inverse transformations, or inverse transformation theorem. So in this video, we are going to discuss an example of this bivariate transform using the bivariate transformation theorem. So let's get started. Our problem is that we have x and y that are standard normal distribution or random variables, or they have a standard normal distribution. We are interested in the transformation x divided by y. We're going to call that u. Now, for the transformation theorem, we have to have two relationships. We have to have one for u and one for v. Obviously, we could call it any letters we wanted, but in this video, this text, we're using u and v. So remember that IID says independent and identically distributed. This independence will help us be able to get the joint PDF of x and y. So if this is a in-person class, then this will be following an in-person lab inside the classroom. If you are attending a purely online course, then this is part of the lecture series. Okay, so what we want to do is we want to find the joint PDF of u and v. So our hint here is that we need to introduce a dummy variable, v, such that the transformation from x and y to u and v is 1-to-1. We want to choose something really simple. So we need something, the simplest thing we can do is we can look up here at the denominator and we can say, let's let that be v. And this is the pattern you will see when you have ratios, that you will have u is some ratio, then whatever the denominator is, you'll want to choose that as v, and it works out very nicely. So this is something that works repeatedly, okay? So the choice we have is v is equal to y. Now, I want you to notice that we have u is equal to x over y, and v is equal to y, okay? So when we go to solve our inverse transformations, we're going to need x in terms of u and v, and we're going to need y in terms of u and v. Okay? So that's why it's called an inverse transformation. Now, remember that the standard normal PDF has this form, f of x equals 1 over square root of 2 pi e to the negative x squared over 2. Because the mean is 0, we have x minus 0 squared, negative x minus 0 squared, over 2 sigma x squared, but sigma x squared is 1, so we just have a 2 on the bottom, all right? So that's how we get the standard normal PDF. And it's not complete unless you specify the range of x. And y being identical also is a standard normal distribution with mean 0, variance 1. And so everything's the same here in this second equation or PDF, except that we've switched out x with y. So everything else is identical. And that's what it means to be identically distributed. They have the same distribution. However, we usually use different letters to represent the different random variables so that we don't confuse them. And then we need the joint range of x and y, which is x is in the real numbers and y is in the real numbers. And we're going to find our inverse transformations. I always start with the simplest one. The simplest one in this case is we had v equals to y. The inverse transformation of that is that y is equal to v. So pretty simple. And then we do the more complex one. So we need h1, which is solving for x. And so in u equals x over y, multiply both sides by y, and we get x equals u times y. Then we can use our substitution for y, and we have uv is h1. So we have v, h2 is equal to v, h1 is equal to u times v. Now, where it becomes tricky, or can become tricky, is finding the joint range of u and v. So what I've done in this situation is I have taken x and plugged in for x the inverse transform, which is uv. And for y, I've plugged in its inverse transform, which is v. Well, y is simple, it's done. But to get u by itself, we need to divide by v in this expression. And then we need to keep in mind that we're looking at limits, basically. We're trying to see not really at infinity, but close to infinity, what's happening. And when we plug in v, which is between negative infinity and positive infinity, if v is any number less than infinity, which is a real number but positive, then u has this relationship. Okay, so if v is positive, large, any positive number, as large as you want but not infinity, then the relationship holds. Now if you make v negative, again not equal to infinity, but as big as you want, that's not infinity, and you divide these values by negative v, then, or negative value, which is v, then you get a positive over here and a negative over here, and you flip them and you end up again with this expression. And of course v is direct. However, we notice that we don't want to divide by 0, so we could break up v this way. Now, in statistics, when we have this situation, it's a single point, or a single point of y anyway, the probability that the only problem we have is when x is equal to 0, or u is equal to 0, and y is equal to 0. Okay, so x is equal to 0, y is equal to 0. That's an issue. That's when we have 0 over 0. And we'll notice that because these are continuous distributions, remember that anytime we have an equal to sign for the probability, then that probability is 0. Because for the univariate case, we need area under the curve, and a line has no area. In the bivariate case, we need volume in the slice, but if there is no width to the line, then volume is length times width times height. One of those is 0, then we end up with 0 volume. So we do not, since we know that this probability is 0, it's unlikely to happen, so we don't make this a complicated range. Do not make it a complicated range for v. So we go back to just u is between negative and positive infinity, v is between negative and positive infinity, and we probably make a note to ourselves that, oh yeah, v is not equal to 0. Now, since x and y are independent, we can easily write the joint PDF of x and y. F of xy is equal to the marginal of x times the marginal distribution of y. And we know what those are because they're standard normal. So we plug in and we combine or simplify, and we end up with this expression. And don't forget that x and y is in A. All right, so that is your joint PDF. Now, we need to use our inverse transformation theorem, and it states that we need the Jacobian. Recall that the Jacobian is a determinant of a matrix. Determinant. These are not absolute value signs. Because this is a matrix, what looks like an absolute value sign is saying take the determinant. In our transformation theorem, we need the absolute value of the Jacobian. But to write that would put two lines. If I put the absolute value of j, then I'd have two lines here. The first is for the determinant, and the second is for the absolute value, and it would be very confusing. So we do this in two steps. So you can think of the Jacobian in one of two ways. You can think of it in terms of x and y, like some authors do, or you can think of it in terms of h1 and h2. So I find that students get less confused when I use h1 and h2. And so we're going to take the derivative of h1 with respect to u. And so when we do that, v is constant. It's considered a constant because we're ignoring that v is a variable. We're only looking at u, just like we do when we do a double integral. We integrate x and y. Whichever one we integrate first, we treat the other as a constant. We don't worry about it at this point, except just it acts just like a constant. So we have h1 is equal to u times v. So if I want du of h1, then that's going to be v d du of u, well, du is 1, and this is just v. Okay? And so that's what we have here. And then I take dv of h1, and that's going to be u times dv of v, and again I get u. And so that's here. Then I have h2 is equal to v. So when I take du of h2, there is no u here, so that's going to be 0. And when I take dv of h2, that's dv of v, and so that's 1. Now to calculate the determinant of a 2 by 2 matrix, that's very easy. It becomes much more difficult as soon as we go to 3 by 3. But for a 2 by 2, we're using this first diagonal, and we'll multiply the elements, v times 1, and then we subtract the product of this other diagonal. So v times 1 minus u times 0, which is just v. Okay? And so we have v is equal to our Jacobian. Now, again, we need the absolute value of the Jacobian, so we have to take the absolute value of v. Now, v is between negative infinity and positive infinity, so we cannot remove the absolute value. Okay, so we cannot remove the absolute value. Now we're going to use the transformation theorem. And remember that the transformation theorem, and this is V, sorry about the typo, is f of h1, h2 times the absolute value of the Jacobian. And remember that h2, we're going to substitute that for any place that we find x, and for any place we find y, we're substituting h2. So h1 for x, h2 for y. And so we go back up to our joint PDF of x and y, and we substitute in, this was x squared plus y squared, so we have uv squared plus v squared, times, so that's in the exponent, times the Jacobian, the absolute value of the Jacobian. So we can simplify this a little bit by taking our exponent and distributing it across u and v. And so we have u squared v squared, that's supposed to be a v, plus v squared in the exponent here. And then we have to say that u and v are in B, the joint range of u and v, okay, which we specified earlier, which is the xy plane, okay? Now, we see that u and v, their joint space, uv, is the xy plane, or the uv plane, the uv plane, which is a rectangular, so we have a rectangular support of for u and v. So we could have an independent marginal distributions. We could have independent marginal distributions. I'll say it right in a minute. Okay. So to get the marginal of u, because that's the one that we're really interested in, right? But we will get the marginals of both. Now what we want to do, the strategy here is we don't want to have to evaluate the integral unless we have to. Because remember, with the normal distribution, you have to use polar coordinates many times. You might be able to use a u substitution for the expectation, but it's usually a very tedious and involved process that takes a long time. So we want to avoid that if possible. So we use the general notation first. So g of uv dv and integrated from negative infinity to positive infinity. And it turns out that u really does have a support from negative infinity to positive infinity, so we don't change those when we come over to the and plug in for the PDF g of u and v, right? If it did have different limits, then we, at that time, for the support, we would plug them in, okay, as we'll see in another example later. So I can pull the 1 over 2 pi out as a constant, and then I have e to the negative v squared u squared plus 1 over 2. And then all of that times the absolute value of the Jacobian and dv. Now what I want to do, since I don't want to have to evaluate this integral, I want to take this and make it look like a normal distribution somehow. And so if you remember what the PDF of a normal distribution looks like, f of x equals 1 over sigma x square root of 2 pi, and then exp of negative x minus mu squared over 2 sigma x squared. And I can say mu x here. Okay, so we're going to try to get it to look something like this. We've got 1 over 2 pi, so it's easy enough to get the square root of 2 pi. Remember that we're taking the integration with respect to v. So u is a constant. So I want v to be my variable. I need v squared, that's negative v squared, to be on the top by itself. And then I need to take this and put it in the denominator so that I have 2 times sigma v squared on the bottom. Well, to do this is a little algebra. What we can do is we can multiply. We're factoring out the u squared plus 1 from the top, and we can move it to the bottom by taking it 1 over that. It's an inverted fraction, but I'll work it out a little simpler than that. I can take negative v squared u squared plus 1 over 2, and I can multiply the top and the bottom by 1 over u squared plus 1. And so this cancels in the numerator, and I'm left with negative v squared over 2 times 1 over u squared plus 1. And so this 1 over u squared plus 1 is going to be sigma v squared. All right? Now let's see, and you can see that I have that substitution here, and we're wanting to make this look like the CDF of a normal random variable. And so here I've made the substitution for sigma v squared, and really then what I need to do is I need sigma v times square root of 2 pi. Okay? Now remember that the square root of 2 pi times the square root of 2 pi equals 2 pi. So I can break up 2 pi into 2 square roots here of what I need. So that's what I've done. We have 2 pi, square root of 2 pi here, square root of 2 pi here. We're going to keep this separate because we don't want to cancel this out or to simplify it. We're trying to make this portion look like something to do with the normal distribution. Now, I didn't have sigma v, but I needed sigma v. See, here's my format or pattern, if you will, from up here. So I need this sigma v down here. To get the sigma v down here, so I'm dividing by sigma v, then I'd need to multiply by sigma v. So if I wanted to, I could cancel them out. I'm not going to cancel them out because I'm doing this so that they look like, I have something that looks like a normal distribution. And what I have is 1 over sigma v square root of 2 pi, and then I have the integral, and I can move the absolute value of v up here, and then I have e of negative v squared over 2 sigma v squared dv, and I could rewrite this as 1 over sigma x square root 2 pi, or this is sigma v, sorry. So, and I'm just using the part that's in the bracket here, this part here. I'm just looking at that. So 1 over sigma v square root 2 pi, and then I have the integral of negative infinity to positive infinity. So what I'm going to do is, wasted a little time here, I'm sorry. So what I'm going to do is I'm going to first move this inside, square root of 2 pi, inside the integral. And then, but I'm actually going to make this absolute value of v first, and then 1 over sigma v, square root of 2 pi, e to the negative v squared over 2 sigma v squared dv. This is f of v. So this is equal to absolute value of v, f of v dv from negative infinity to positive infinity. This is equal to e of the absolute value of v. And so we need to evaluate that, and we don't have to use the integral to do that. We know what the expected value is. You might use, well, I don't want to give you too many hints because this is homework for you. So the hint is don't try to evaluate the integral. Again, find this value. So this is homework. Find this value by the expected value of the absolute value of v by using the integral, looking at it, looking at patterns, and also use the definition of absolute value. That's going to help you. You're going to have to break it up, and that's all the hints I'm going to give you. But the answer comes out to sigma v times the square root of 2 over pi. And so once we know that, we plug that in to this here, and so that's what we have here. We've plugged it in. Whoops. And you'll notice that these combine to sigma v squared. This 2 and this square root of 2, those cancel. Remember, I can rewrite this square root of 2, square root of pi. And then I have pi on the bottom. So this gives me this expression, sigma v squared over pi. I substitute back in for u, and I have a PDF that I don't recognize because we haven't gone over it yet. You won't recognize it. I do, of course. So this PDF is actually a very important one as well. And we call this the standard Koshi distribution. And this is the Koshi 0, 1. So I'm going to skip down to our result. Our result is that if x and y are IID, standard normal, then the ratio of x and y is a Koshi 0, 1. Okay? So that is how we are evaluating this. So it becomes a standard Koshi, and I will go over the Koshi distribution in the next video. So please don't forget to scan and upload your lecture videos by midnight of the date listed on the course calendar. If you have questions, come to virtual office hours. If you can't make it to virtual office hours before you need an answer, then email me. But I need you to email me 2 things: a picture of your work so I know how you're approaching the problem, and also a picture of the problem because I may not have that available when you email me. Okay? So please take care of yourself, stay safe, and we hope to see you next time.